We are getting into the last kind of data analysis for your final lab, strain gauge lab. So in this lab, we're working again with cantilever beam, just like in the last video, half Wheatstone bridge, strain gauge 1 at the top, strain gauge 2 on the bottom of our beam, and we know kind of our expression for kind of final bending. So we have the equation below. Again, we're going to be working with delta displacements of 0, 0.1 inch, and 0.2 inches. So the beam at a given x value where the beam is secured. So again, x is going to be equal to 25.5. Basically, you're going to apply the deflection at x of equal to 25.5 centimeters away. And then again, L is the length of the beam, y is our Young's modulus, 69 times 10 to the 9 gigapascals, or excuse me, 69 times 10 to the 9 pascals. P is going to be our applied load, which we're going to have to solve for. L is the length of the beam, so the beam is 30.5 centimeters long nominally. The width of the beam is 25.5. Thickness is 6. Again, nominally, I made these measurements with a ruler with millimeter tick marks. All dimensions are made with the same ruler, and I only measure these values once. The displacement delta is performed with a micrometer with a resolution of 1 micrometer. So the displacements, or delta, so some uncertainty in delta could be 1 micrometer. So in this lab, we're going to apply that deflection that 25 centimeters away. Here's the moment of inertia. Here's some kind of equations as well. And let's go ahead and get into this. All right, so we have our displacements. So we can solve for the theoretical strain with the following equation. So one of the unknowns is going to be this load P. So we're going to have to solve for P using the kind of above equation. So that's what I'm going to kind of do here. So I'm going to look at the strain theory. So this is my strain theory equation, and then I'm going to calculate. So there's going to be uncertainties here, but again, I want to plug in. I'm going to solve P from this equation here, their delta. So let's look at delta, and we're going to kind of rearrange that expression. So I'm going to solve for, and actually, I'm just going to make a new equation. So I'm going to clear this. So I'm going to clear. Let's say that this value is this. I'm going to solve. And just rearrange this expression. Solve. I'm going to clear my notebook. I'll call here. Solve delta delta as a function of P. Let's get this. Actually, I want to plug in my moment of inertia, so I am going to plug in that there. So I'm going to express this thing here. So I'm going to plug in for P this expression right here. So I'm going to do make a function called, because I need to take these partials again. So strain theory. Actually, I'm going to do strain partials. Strain partials equals this equation here. I'm just going to sub in for P as a function of all these different variables. So let's go ahead and look what that looks like. Actually, let me undo that here. I'll copy this. So here we go. Plug in for P here. And we get this expression for strain partials. So now my strain theory, again, this is strain theory just plugging in for here, but I just want to keep this value here because I'm going to be solving in for P and then plugging in. Again, it doesn't really, make a huge difference, but I'm just going to set up the notebook that way. So now we can see, again, this is just to visualize, look at my function, my strain theoretical is a function of several independent variables, D, delta, H, X, and L. So I'm going to need to take partial derivatives of all these different parameters. So I'm going to have to do D of, strain partials as a function of X. I'm going to have to do D of strain partials as a function of delta, et cetera, et cetera, et cetera. Ooh, not delta. Like this. And all of these, again, what's the uncertainty in delta? Well, we had this basically a resolution of a micrometer. H, D, and H, D, L, and X, they're all measured with these uncertainties that are associated with the, again, your millimeter tick marks. So again, you want to kind of think about these values and plug in. So you need to solve again for the theoretical strain. We measured this one time. So the only contribution is going to be this bias error, this bias uncertainty. So that's what you're going to kind of solve for and kind of work with in this lab. So that's how you're going to take and deal with the strain theory, and you're going to plug in these different values of delta. All of the rest of these values are fixed, as you can kind of see here, and that's going to kind of be essentially the load that you plug in. So you could use the strain partials equation. It's, again, that's going to calculate your strain. But you also want to kind of be able to kind of plug in for the load. But again, you could plug in and you could, again, get the strain from this expression right here. So you're going to solve, or you're going to plug in for different values of delta. So 0, 0.1, and 0.2 inches. Now remember, convert everything here to meters. That is very, very, very important. Meters, Pascal, SI units. That's what we want to be working with in this lab. So from that, you'll be able to kind of get, you plug in those values, you'll get your strain theoretical, and that's about it. So plug in for P, exactly. Now, for the frequency lab, we are going to get the seminal plot that we are going to be developing in this lab is just like we had for frequency. We had frequency, resonant frequency as a function of length. We're going to have strain as a function of delta displacement, and you're going to have your theoretical and your experimental and see do those uncertainties overlap. For the experimental values, we are going to use this expression like we just did in the last video. Epsilon 1 equals epsilon 2, bending. We know the excitation voltage VI is 5, the gauge factor is 2. So there's kind of this there's not going to be any bias error in F and no bias error in the excitation voltage. However, the resolution in our voltage amplifier, which is going to determine this delta V, is going to be, like I said, microvolts. So we need to measure or look at our experimental measured voltage, which is measured in volts. So this starts with the excitation. This is how we're going to calculate the strain experimental. And now I'm going to import some of the values. So I'm not going to go to internet. I'm going to go to my desktop where I've already extracted all my data for strain. And you can see here, these are the delta. So 5 repeats of experiments. Again, you could kind of, it was sampled at 10 samples per second. So make sure to plot, some of the plots that you might want to include here are, you could include some voltage plots. It's not necessary, or not incredibly necessary, but you might want to include schematics. I think would be very helpful in this report as well. So you could do delta V naught as a function of time. Again, 10 samples per second for 10 seconds. So you can kind of include some of those plots, but this is kind of the big seminal fundamental plot. Schematics of kind of what's happening in this lab and explaining how you kind of go through your equations, similar to kind of what I've drawn here, would be very, very helpful in your lab report to understand it. So let's go ahead and look at the first data set. So this is my delta displacements. So 0 inches, 0.1 inches, 0.2 inches, and then 5 repeats. So let's look at the first one. So if I apply a 0 displacement, why am I reading a voltage? We know from our Wheatstone bridges we should be at balance. Well, the problem is when I push really hard on my strain gauge, I actually, I'm pretty sure I've already pre-strained that material. So it's very, very hard to get kind of this value to be completely null. So we're going to have to kind of do our own type of baseline. So we are going to have to take the change, this delta V, the change in the output voltage. So this is the output voltage of a strain of 0. So a strain of 0 must have a delta V, a change in output voltage of 0. So we're going to have to multiply it by this kind of baseline measurement. So for example, I'm going to take my mean of 0 is going to be mean of delta 0 inches right here. So that's the mean value right here. And again, you do the same exact kind of procedures before. So 5 experiments. So take the mean of each data and then do the standard deviation of those 4 measurements and then take the mean, or you'll basically do this multiple times with your 5 different data sets. So you're going to have 5 means. Take the mean of those means. That'll give you your point on your axis. Take the standard deviation, calculate the precision error. So you're going to have a precision error here that is going to be, again, in volts. So we want to make sure that we kind of correlate that or actually divide out and keep that in percentages so that we could kind of do this analysis. So make sure that you consider that as you're going through experiment, as you're trying to kind of figure out what's the total uncertainty. So this is precision error in voltage. We need to be able to normalize that and convert it into strain. So make sure that that's the case. Now, I'll take this value here and I'll do the same thing for my, basically for my 0.1 inch. So delta O1, and I'm just going to plug in here just to kind of give an example here, here, and then we'll do the same thing for delta 2. And then here, delta 2, and we're going to get this expression right here. Then remember, this is just for one data set. You're going to have to do this for all 5 of them. So you're going to have to find the 5 means, take the mean of the means. I'm just doing one quick example of what you might expect. So remember, and precision error is in voltage here. Be very, very careful. Mean of 01 is going to just be mean of delta 01 inches. And I'm going to do my M02 is going to be equal to mean of delta 02 inches. Now, so the change in voltage, so my delta V of zero deflection is going to be M naught M0 minus M0. My delta V01 is going to be equal to M01 minus M0. And my delta V02 is going to be my M02 minus M0. So those are my delta V naughts. I could now plug that into that expression, so I could get, for example, let's just make sure strain experimental slash dot delta V. Let's make sure that's the equation up here. Delta V capital. Delta V goes to this delta V naught, and as we might hopefully expect, that strain is going to be equal to 0. It better be. And for here, we're going to just again change in output voltage is this. So that's going to be our strain, and then now we can look at this value right here. So that would be again your corresponding, that nominal value of kind of strain. So I'm going to do delta V not 2. Those are your values. Now we can also get the kind of experimental values here. So let's go ahead and pull this equation down. So, and let's kind of plug and chug into here. Here. It shows us, and let's try to plug in for some values. So let's do strain partials slash dot. Let's do the first one. So actually, since we have strain delta V naught 2, I'm going to substitute in for, let's replace, okay, we know that D is equal to 25.5 minus 9.5 times 10 to the minus 2. That's going to get us into meters. We know that the H is going to be equal to 6 times 10 to the minus 3. We also know that our X is going to be 25.5 times 10 to the minus 2. We also know that our L is going to be 30.5 times 10. 3.5 times 10 to the minus 2. And what else do we have in here? D, delta, and then our delta, of course. So delta is going to go to, for this particular instance, 0.2 inches times 0.0254 to convert to meters. And, oops, I think I have too many. Don't want that. And so this is our value. So you can see right here, this theoretical strain is pretty close to this experimental strain derived here. Is within error bars. That's what you're going to have to figure it out. So one other thing, obviously, again, you'll have 5 data sets, so you're going to have, again, uncertainty in volts here. So you're going to have to, non-dimensional, or you're going to have to make that a non-dimensional fraction, divided by the nominal value, and then you'll be able to multiply by the nominal strain in order to kind of convert back. Now, do we have bias here? Well, yes, because it says that we have our voltage amplifier has this uncertainty. So we're going to need to take this strain equation and do derivative of strain exponential as a function of delta V, and we're going to have to multiply that by some uncertainty that's given right here. So for the experimental, there will be bias, and then there will be precision. For the theoretical, there will just be bias error. There's no precision. There's no multiple measurements. So that's it. Do this. Create those plots, those kind of key seminal plots that we kind of outlined here, and then that's it. You're done with you finished Engineering 110 lab. So congratulations, and then I'm looking forward to reading your lab reports. So let me know if there's anything that I could do to help. Email me. I'll be available before and during Thanksgiving. again, take some time, stay safe, most importantly, and then again, congratulations, you finished Engineering 110 Lab. I hope it's been, again, these are difficult times, but I appreciate everyone who's kind of stuck around and battled through this remote learning and more data analysis kind of lab component. And again, if you're interested in any of these labs, I'd be happy to kind of show you in person, and I will be doing so next semester. And I'll be posting some kind of basically GoPro video footage of how these labs are actually performed. So if you're still interested, I'll be happy to show you at that point. So I'll see you hopefully in another class. Thanks. Bye.